So hello everyone again, and Bismillah. In this video we are going to implement the PID controller that we have previously designed for this plant. Now the PD controller are still the same for now, and we will be adding the I or the integral action to this controller in order to have the complete PID controller. You know that the integral action is simply a coefficient, a constant coefficient divided by s, which is the Laplace variable. And this is simply a transfer function. So let's just have a transfer function. It's a causal transfer function. No need to use, like we did in the derivative action, no need to use something else. Another block. No, we use the standard transfer function block. And its denominator will be 1 and 0 in order to have a single s in the denominator. However, its numerator is, we were able to choose any value between 0 and I think 130. So we started by 2. Let's just have a 2. Have to right now. Then looking at the response of the system, we may change this. We will add a third plus to this, maybe in here, to this block. Now it's not that cool, but we will go with it right now. Yeah, by this we have constructed the full PID controller. This is the integral action. This is, these both combined are the derivative action, and this is the proportional action. Now just let's run this system and have a look at its response. Okay, we see that the overshoot of the system is, it's even a minus overshoot. This is not that kind of reasonable, but yeah, it's almost 0.919. The rise time, however, has risen, and this is not a good sign because we added the integral action. The addition of the additional pole, has caused some things to be changed in the system, but it's still in the acceptable region. It's still almost 0.5 seconds. The amplitude, however, is a very nice amplitude. You can see that the amplitude is 9.61, 0.961, of course, and this is very close to 1. Now let's just try to change this and put, for example, 4. Let's just put 4 in here. What will happen? If we put 4, we will have, that's even better. Look, 9, it's 0.983. It's very close to 1. But the error that we are having from the system is still more than 1%. So we may add it again, we may increase it again, sorry. Let's just put it as 8 and have a look at the new response of the system. Now, yeah, that's very nice. The amplitude of the system is totally 1, which is a very, very nice amplitude. It's totally what we want from the system. And the rise time of the system is less than half a second. The overshoot is less than less than 5% of the reference. This is a very nice system that we are having right now. It's almost a perfect system. Using a PID controller, we were able to achieve such a system. Now I'm just willing to show you something. Like if we increase the simulation time, this is the shape of our response. Look, the steady state response of the system is always 1, which is a very nice thing to have. In here, when we increased it, we had, it's almost 1% error, but it's still in the acceptable region. It's a very nice response. The overshoot is almost 5. It's less than 5%, which is also in the acceptable region. And the undershoot of the system is, sorry, not the undershoot. We are willing to look at the rise time. Yeah, the rise time is less than half a second. It's a very nice system. It's a very nice and acceptable system. Now, let me just show you the effects that are caused by the coefficients of this PID controller. Now, if you increase the proportional action of the system, the proportional coefficient, increasing the proportional coefficient will lead to an increase in the overshoot. And at the same time, if you increase it very much, let's just increase it to be 40, for example. Let's put it 40, and okay, let's run the system and have a look at the scope. Yeah, you see that the overshoot of the system has risen a lot. It's now 11%. Okay, the rise time, however, gets decreased when you increase the proportional action. Okay, so the overshoot gets increased when the proportional action is increased. The rise time gets decreased when the proportional action is decreased. And the transient response of the system, the transient response gets worse when the proportional action is increased. But let's go back to 20 and try to increase the damping or the derivative action of the system. Let's make it 8, for example. I'm just throwing numbers. Now, looking at the response of the system, you may notice that by increasing the derivative action of, the derivative coefficient of the system, the damping of the system increases. meaning that the rise time will increase because there is more damping in the system, while the overshoot of the system will decrease. With respect to the previous overshoot. Now the damping has increased, the overshoot has been decreased. Okay, while if we go back and increase the integral action, let's just put it, for example, let's make it 80. Now this integral action is actually having some destabilizing effects on the system. So now the transient response will be very much, yeah, you can see that the transient response of the system has increased a lot. It's very bad right now. We have a sinusoidal response. It's decaying. I mean, the sinusoidal effect is decaying because the system is still in the stable region. But for sure the rise time will decrease because of the increase of the integral action. The integral action is very similar to the proportional action, but it's also having some destabilizing effects because it's adding an additional pole to the system. So if we make the integral action way more than is acceptable, for example, let's make it 400, the system will not be stable anymore. It will be unstable. It will be an unstable system. Yeah, you can see that the system is an unstable system right now. It's not bistable at all. It's an unstable system. It's going to infinity. You see that the scale of this scope is 10 to the power of 50. So you have to be in the margin, in the interval that we have extracted between 0 and 130, roughly. You may violate it roughly if our analysis was not that accurate. You may violate that interval roughly, but try to stay inside that interval. So by this, we have actually summed up the topic of PID control. Thank you for listening, and see you in upcoming videos.